Now that we know how to calculate work in compressing or stretching a spring using integration, let's look at an actual example. So here we have this problem here, and they're really giving us two pieces of information in that problem. If you read the first part, it's really just telling us about the force required to stretch it a certain amount. And remember, part of this integral is K, that spring constant. And they're really telling us in the beginning there that a 20 Newton force is required to stretch the spring from its natural length of 5 meters to a length of 7 meters. So that's telling us something about K, right? So from that first bit, we know that from Hooke's law, force is K times X, right? And we're told that for this particular spring, 20 newtons will stretch that spring from its natural length of 5 meters to a length of 7. So that's 2 meters of stretch, right? So X is 2 meters. And now just solving for K, K is 20 newtons divided by 2 meters, or 10 newtons per meter. So now we know our K for this particular spring, and let's see what these units are telling us. What this is telling us is every 10 newtons of force that you apply to that spring, you'll stretch it another meter. So imagine this spring was hanging from the ceiling and we hooked a 10 Newton weight on there, it would stretch a meter. And then if we hooked another 10 newtons on there, so we had 20 newtons on, it would stretch another meter. So every 10 newtons of force you can think of as a weight pulling on it, it would stretch it another meter. So that's why those units make sense there for K, that it's newtons per meter. Okay, so now that we have our K, we're ready to do our work integral here. So this is, now we got to be careful about remembering what X is, right? X comes from Hooke's law, which X is amount of stretch. So when we look at the statement of the problem there, the spring goes from a length of 6 meters to a length of 10 meters. Well, natural length is 5 meters, right? So that's 0 amount of stretch. 6 meters would be 1 meter of stretch. And then we're stretching out to a length of 10, which would be 5 meters of stretch. So X is measured in amount of stretch always because Hooke's law says that, right? Hooke's law says it's proportional to the amount of stretch. And so X needs to be amount of stretch there. And then we got our K already. It's 10 X then dx. And now, simply integrate. That'll be 5x squared from 1 up to 5, or I'll take the 5 outside. 5 squared, 25, 1 squared, 1. 5 times 24 is 120. Now, we should always, in these physical problems, label our units. So what would our units be here? Remember, work is a force times a distance, right? Or force times displacement. Our force units here were in newtons, and our distance units were in meters. So this should be Newton meters, or remember, in metric, a Newton meter is a joule. So 120 joules in this case. So be careful on your limits. The most common mistake would be to just say, well, I'm going from 6 meters to 6 meters to 10 meters, so I'm going to go from 6 to 10. But that's not how much it's been stretched. The spring itself is already 5 meters long just laying there. So it's only 1 meter to 5 meters of stretch.